All right, so we've got the immune response. We are doing a very, really a thumbnail. We're not getting into every little bitty aspect in the immune response because honestly, it is pretty immense, the amount of stuff that goes on, the amount of material that's in this chapter. And like I was saying last time, we had another class with another professor who has moved on. And her PhD was in, some immunology stuff. So she did a lot of this in her class. Now that she's gone, I honestly don't know what the next professor is doing in terms of this. So I've added a little bit more than in the past when it comes to the immune response, just a few more players involved to kind of get an understanding of the massiveness that is the immune response. And two, another thing that I'm not going to necessarily get into a whole heck of a lot. I mentioned it, but it's the stress and inflammation is a part of the immune response. So if you are in a stressful state, you can actually kind of prime up the immune response, which is not a good thing because now when something bad, foreign invader, enters you, you have to rev up your immune response even more to mount it. Inflammation is the same thing. And inflammation can exacerbate the immune response. Okay, so if you have inflammation, what happens when you do have a true invasion? Bacteria, viral, parasitic, whatever. Well, now I have to rev up the immune response even more. So stress, pro-inflammatory society that we live in, diet and whatnot, can really kickstart the immune response when you shouldn't be kicking in the immune response. Okay, and it makes it difficult to fight things, and you're more prone for infections and the downward spiral that is poor health. So there is a lot that goes into this, and we're just going to look at some of the major players, some of the major bits and pieces, and some of the major types of immune responses that we have. Big picture. We're not going to get into all the complement pathways and all of that whatnot. We'll mention a little bit of it, but we're going to try to keep it simple. As simple as I can live with myself, right? Who is doing the immune response? We talked about this when we looked at blood and introduced white blood cells. We talked about this the other day with the lymphatic system, and we're going to mention it here. So hopefully I'm taking this nail and I'm driving it home in your tiny little heads here. White blood cells, leukocytes are going to be the major cavalry involved in mounting the immune response. As with all blood cells, all of it starts in the red bone marrow, okay? All starting with that pluripotential stem cell. And then different factors are released into the blood, and the bone marrow picks those up, and then it takes that thing and turns it to a red blood cell or turns it into a white blood cell. We talked about that way long ago, right, when we talk about blood. We have granulocytes and we have agranulocytes, okay? Neutros, eos, and basos, those are our granulocytes, okay? And the monocytes and the leukocytes, they are my agranulocytes. No granules, no visible granules within them. Excuse me. Monocytes can flow in the blood. They can flow in and out of tissues. When they leave the blood, a monocyte, and enter the tissues, they become a macrophage. So what is this going to tell you that it's doing? We're all chomping up stuff, right? It's going to engulf it, going to try to kill it. That doesn't sound very specific, and it's not. We have our lymphocytes, B cells, B lymphocytes, T cells, T lymphocytes, and then what we call NK cells, which are natural killer cells, all right? We'll look at a little bit at what all of these do, obviously. B cells, if you want to write underneath it, these guys are going to be making us antibodies, think we've mentioned that a handful of times. T cells are going to be engulfers of foreign invaders. Natural killer cells can do a multitude of things. They're kind of an immune surveillance cell. They just travel around, enter in, get back in the blood, enter in tissues. They're looking for cancer cells. They're looking for cells that are running amok, non-functioning cells. So these are kind of immune surveillance, and they kind of do a whole multitude of things. They've done some interesting research with them to try to maybe manipulate them so where they look for a specific isotope, inject that isotope into specific cancerous tissue, and have the natural killer cells target those specific tissues. So there's a lot of research that has been there going on with natural killer cells, and I always find that very fascinating. Where do we find our white blood cells? Well, generally, they're very small in numbers in blood, typically. Okay? Unless you go in and give blood and you're mounting an immune response, they're generally much lower on the totem pole. Again, the biggest component is going to be red blood cells. These things are found in tissues, right? And we talked about this the other day with the lymphatic system, where they're created, where they start to mature, and where they become immunocompetent. Made in the bone marrow, right? Both B cells and T cells. T cells leave there, go to the thymus, hang out for a while, become mature. They then leave and go to all of those secondary structures, lymph nodes, spleen, okay? Malt type tissue. And they go and hang out there. When they get exposed to those things, they become immunocompetent and can mount an immune response. T cells, B cells, macrophages, dendritic cells, natural killer cells, all of those things hanging out. Sometimes they can be permanent. Sometimes they migrate. We have specific cells in the liver, Kupffer cells. They're a macrophage that stay in the liver. We haven't talked about it yet. Talk about it in the next unit. We have macrophages that just hang out within the alveoli. So when you inhale foreign invader and it gets in there, we have a dude right there ready to kill. And that's the alveolar macrophage. And we have a number of these macrophages in a number of different locations just hanging out within the tissue. It's not necessarily a monocyte that gets released into the blood and looking for the chemical that it's attracted to and then enter into the tissue, okay? Some migrate, some always stay. That's all I'm trying to get across there. If I did ask a question, maybe it's one multiple choice question. Nothing too big there. As we will see here in a little bit, we're basically going to have 3 layers or 3 barriers, I guess is probably the better way to think about it. 3 barriers of protection when it comes to preventing foreign things from entering us or gaining a foothold within us. One of those barriers is going to be skin. Excuse me, guys. One of those barriers is going to be skin. As you can see here, we have a number of dendritic cells in skin. Specifically, we call those, hopefully you remember this, Langerhans cells. Langerhans cells is a dendritic cell within the layers of the epidermis. So we saw those kind of way back when. These dendritic cells are usually derived from monocytes. If you must know, I'm not going to ask it, but monocytes, dendritic cells are an offshoot of those guys. We find a number of dendritic cells in that first barrier, skin. And skin's closest to the outside world, right? Whether this is here on my arm or inside my mouth, anything with an opening to the outside world, right, has a vast epidermal layer to it. This is going to be your first contact with a foreign invader. So if for some reason a foreign invader breaks through the skin or swallowed, inhaled, whatever the case may be, we have dendritic cells that are going to actually see it first. And in most cases, do a good job of handling those foreign invaders. Excuse me. We have a number of what's called mast cells right underneath the epidermis in that connective tissue. More internal. So as we start to get deeper into the body, we have another layer of protection, a group of cells. They usually stay near, as you can kind of see there, close to blood vessels for a number of different reasons. One of those is if we get too far away, what won't be able to occur in a connective tissue? Does anybody remember? Starts with a D.
Diffusion.
Diffusion. Good job. The further you get away from blood source, the more difficult diffusion is. So if we have these mast cells, they're generally kind of in higher concentrations around those small blood vessels or capillaries that you find within that, connective tissue layer, dermis, whatnot. So they're going to pick up on chemicals. They're going to be able to release chemicals, okay, just as easily as well. And this is going to alert the body when it's come into contact with a foreign invader. And what we will see here in the two different types of immune response that the body has, it's all about the chemicals, man. Always about chemicals. Chemicals are what allow the cells within the body to know there is a foreign invader, and then it knows where to go. It's also chemicals that our cells release that say, hey, I need help. And we mount an even greater immune response. So it's all about chemicals, man. Okay. And hopefully that makes sense to us that mast cells need to be closer to those blood vessels because of diffusion, getting those chemicals into the blood or picking up on those chemicals. Again, dermis, the mucosa of anything open to the outside world, respiratory tract, gastrointestinal tract, urogenital tract. All of these are found with an opening to the outside world. I said that a lot in the lymphatic system. You see it a lot here. They're also found in the connective tissue around all of the organs as well. If it does get in and it does get into the blood and travel around, it can get into tissues or organs. So we'll have mast cells in various different organs as well. Okay. The last major, I believe, yes, the last major player, dendritic cells, mast cells, T cells, B cells. The last major player that we have here are cytokines. And I'm introducing a word here, or two words here now, that we'll be expounding upon later here. Cytokines help regulate the immune response, and it doesn't matter what type of immune response. Okay, it can be a part of the innate or the adaptive immune response. With innate, that's a fancy pants word, right? Innate, you're born with. Innate, you're born with. Born with. Okay. And we're all born with one. Okay, we all have an innate immune response, and we're going to introduce it, I think, on the next slide and talk about that next. And then after that, we'll talk about the adaptive immune response. And this is our ability to learn and adapt. This is antibodies, okay? This is, as we'll see here in a little bit, cell-mediated immune response and antibody-mediated immune response. And that's what we'll be talking about. What did I say it's all about? Drugs, man. Chemicals, okay? These cytokines, how do they regulate the immune system's activity? They release chemicals. Whenever there's a foreign invader that comes in, we have antigens on the surface that let us know when it's a foreign invader. It's also going to be giving off some secretions as well, to be honest, some byproducts. And it's these cytokines that help to see that chemical being released, then mount, well, it help to initialize the immune response. How does it do that? Cytokines do a bunch of fantastic things. They can act on a cell that released it, and we refer to that as autocrine. Auto, self, okay? Auto means self. So these can be chemicals that stimulate the cell. And you're like, what the hell is the cell going to do? Well, I mean, it can kill itself, sacrificing itself for the good of the system. It can stimulate the production of specific protein markers to be released on the surface of the plasma membrane of that cell to cause T cells or B cells to be attracted to it, come to the party, and kill it, or kill the foreign invader within it, thus killing the cell. It can act on cells around it. Para means around. So this is a chemical. Let's say I'm an individual cell. Okay, this is me. Okay, my Chewbacca shirt. I'm the cell. I release some cytokines. Here's a cell and here's a cell. Okay. My head releases a cytokine, and that stimulates these two cells to make it difficult for that invader to get in. So it's going to stimulate the cells around me to be like, hey guys, be on alert. There's something inside of us that's going to hurt us. And so it helps those cells to bolster an immune response, bolster themselves to prevent the bacteria or the virus from getting inside of it and running amok. Cytokines can also be like an endocrine type of secretion, where this secretion gets into the blood and can affect other cells within the system. They have a very short half-life, and honestly, I don't know what it is off the top of my head. I apologize. Okay. But they don't stick around very long. So these things these cytokines are not going to last forever. But once they're in there, the body can start to see them. And by the body, I mean T cells, B cells, monocytes, macrophages, any of our components, dendritic cells, if it's near skin. Any of these components can now start the immune response. And that's what cytokines do. It can be either what you were born with, dendritic cells, mast cells, okay? Or we can get adaptive on this brother and get T cells and B cells activated. So what are the effects? It's the signal, okay? It can signal a lot of different things. Control the behavior of the immune cells. Cause them to start proliferating. Call in specific ones. It can help to regulate the inflammatory response, and we'll see what the inflammatory response here is in a second. Okay, it's part of the immune response. Cytokines, proteins that regulate the immune response, both innate and adaptive. Autocrine, paracrine, endocrine, anything with a crine. Mast cells and connective tissue, dendritic cells and epithelial tissue. We have multiple layers of protection before getting to that ultimate third layer of protection, the adaptive immune response.
On the previous slide, the picture of where the locations of the immune cells, that dark thing by her lungs, is that supposed to be the spleen? It doesn't really say.
Up in here?
Under her lung?
Oh, right there?
Yeah.
Yep, that's the spleen.
Okay.
Yep, that's the spleen. And it's outside of the abdominal cavity there. Very close to those floating ribs, those vertebral type ribs there. And so that's why it's easily punctured, easily ruptured, because it is very superficial from an organ standpoint. All right. So we have innate immunity and adaptive immunity. They differ in many different things. Okay. They differ in cells. Okay. Innate is what you're born with. Skin. Okay. Classic example. And it's going to be those specific components of those barriers. Dendritic cell. Okay. And the specificity of it. Innate is not very specific. Okay. Dendritic cells don't remember that dude that just came last year. So it doesn't produce any memory cells, and it will not produce a quicker response. Adaptive can and does. And that leads us down there to the amount of time. It's the adaptive immune response when you see something for a second time. Instead of taking maybe 10 to 14 days to do the job, it may do it in 3 to 5, 3 to 4, 2 to 4. Okay. It's a hell of a lot quicker. We talk about them individually, but obviously they're all working for the same goal. Okay. If the skin gets cracked and a foreign invader starts to come on in, the dendritic cell will see it, try to mount an immune response. Mast cell will see it, try to mount an immune response. If they can't kill it, they're already releasing chemicals. And we have different structures within, cytokines being one of them. They're going to pick up on those chemicals that those cells release. And that's going to jumpstart T cell activity, which can eventually lead to B cell activity, which is part of the adaptive immune response. Okay. So even though we're talking about these as very distinct entities, innate immunity, adaptive immunity, it's all part of the process. Okay. It is all part of the process. It's just, can you kill it really quickly with innate? If you can, awesome. Move it along. If you can't, well, Then we get T cell and B cell activity, and we kickstart the adaptive immune response. But they are basically both working together. They are both working together. Okay. So innate, you're born with, okay, present at birth, non-specific, major thing there. It is non-specific. This is acquired. Adaptive is acquired. You have to learn how to do that. And the only way you learn is by being exposed to it. Going out in the real world and getting exposed to the creature. What's another way to get exposed and acquire this type of immunity? Anybody think of one?
Vaccination.
Vaccine. What else? Anybody else? There's some moms up in this class. You guys think of anything?
The kids just outside playing everywhere, putting everything in their mouths and playing in the dirt.
Yep. What else?
Breastfeeding.
Breastfeeding. The placenta. Mom can confer immunity to her growing creature within her. Okay. And we'll talk about that when we talk about the adaptive immune response, when we talk about immunoglobulins. Okay. Immunoglobulins are antibodies. It's the fancy way to say it. And as long as you have a placental connection to mom, you get immunity. If you breastfeed, you confer immunity. So there is multiple different ways to be exposed and acquire the ability to learn how to do this fun stuff. Fight off foreign invaders. Innate is barriers. So it's epithelium, connective tissue, membranes. Remember, membranes were a conglomeration of both epidermal and connective tissue. So kind of covers both there. Again, non-specific, and it just is dealing with the creatures in that area. Dendritic cells, mast cells. When it comes to innate, I mean, it's right there in the barrier boundary. So it can be, if it can happen right then and there. It may not actually do anything. And when I say it may not actually do anything, it may not actually be able to kill it completely, like I mentioned earlier, but it is right there. Gosh darn it. I have so many Post-its, they're falling off. Okay. But it can respond immediately, right? It's right in the dang tissue. Adaptive, the players involved there, again, it's acquired, but the players involved are different. These are our T cells and these are our B cells. This is going to be cell-mediated immunity. And I'll use the fancy word, humoral mediated immunity. Okay. T cells and B cells. Okay. And these things can be specific. Okay. These things can create memory. So it can be a much more targeted response. And several days is a nebulous term. If you're seeing it for the first time, again, it can take several days. It could take almost 5 to 6 days to ramp up the immune response. And then it can take another 10 days after that to kill it. If you're seeing something for the second time, this adaptive immune response has a very small lag time, maybe a day or two. And then maybe in the next 4 to 5 days, it kills it. So a much quicker type of immune response here, all right? But the biggest thing, present at birth, learned throughout your childhood, really throughout your life, I guess, best way to put it. Non-specific, versus specific. Skin, connective tissue, membranes, and the dudes or dudettes that are found within those membranes. Dendritic, mast, cytokines. Okay. Adaptive, T cells and B cells. Very specific, very targeted. Can take a few days to get going. And here they both are in a nice little overview here. Okay. Again, non-specific. And this can lead to a whole host of activity there. Okay. Again, dendritic cells, mast cells can release chemicals, and those chemicals the body picks up. It's like the white flag or whatever flag being raised to call in the cavalry. I guess white flag would be defeat. But as you can see, we can have a number of various different things. Adaptive, T cells and B cells. Okay. B lymphocytes make plasma cells make antibodies. And humoral immunity is ultimately antibody-mediated immunity. Humoral means fluid, and antibodies are within the fluids. So that's where that name comes from. It's a very old name. But it's one that a lot of people know.
While you're talking about this, I, for some reason, just have a block with this antigen antibody thing. So is it an antigen is innate? It's either there or it's not. And then an antibody is developed in response to it? Or can you get new antigens?